Good morning to all of you. You know that today we have a very distinguished person with us. He will be speaking on DL Talk today on behalf of IEEE Bombay sections and IIT Bombay. You know that he doesn't need any introduction. In India or in abroad, any IIT, any electrical engineering department, he is so well known that everybody knows him. But I formally introduce him before his talk starts here. Professor Bose held the Conrad Chair of Excellence in Power Electronics at the University of Tennessee, Knoxville, since 1987, where he was involved for teaching and research in power electronics and motor drives. Concurrently, he served as a distinguished scientist and chief scientist of the EPARI Power Electronics Application Center, Knoxville, and prior to this, he was a research engineer in GE Corporate R&D Center and professor of electrical engineering, Rensselaer Polytechnic Institute, New York for 5 years, and a faculty member of Bengal Engineering and Science University for 11 years, 1960 to 1971. He specialized in power electronics, motor drives, especially including the power converters, PWM techniques, microcomputer, DSP control, and applications in power electronics in motor drives. He has been power electronics consultant in a large number of industries. He holds an honorary professorship at Shanghai University, China, University of Mining and Technology, Yan University, Mining University, honorary director, Hong University of Science and Technology. He has published more than 200 research papers and 21 US patents. He has authored and edited several books. In particular, the power electronics and motor drives, advances and trends, power electronics and AC drives, variable frequency drives, modern power electronics by IEEE Press, and many, many other books. Some of these books have been translated into foreign languages. And are widely used in the textbook as university courses all over the world. He has given tutorials, keynote addresses, and invited seminars extensively throughout the world, particularly in IEEE-sponsored activities and conferences. He has served as a distinguished lecturer both IAS and IES Society. Dr. Bose is a recipient of a number of awards, including IEEE Power Electronics Newell Award, and IEEE Millennium Medal 2000, IEEE Meritorious Advancement Award in Continuing Education, IEEE Lame Gold Medal, IEEE IES Eugene Mittelman Award, Lifetime Achievement in Power Electronics and Motor Drives in 1994, IEEE Region 3 Outstanding Engineering Award, IEEE IAS Outstanding Achievement Award, Calcutta University, Mount Gold Medal, GE Silver Patent Medal, GE Publication Award, and a number of IEEE Prizes Paper Awards. He also received the Distinguished Alumnus Award from Bengal Engineering and Science University. IEEE IES magazine published a special issue in June 2010 honoring Dr. Bose and celebrating his contribution in power electronics. I am very happy that today he is with us. One more line I should add, that he happened to be in a time where we are holding an IEEE International Workshop on Variable Structure System, the first time in India. And I'm also pleased to inform you, Dr. Bose is the first person in the world who applied the variable structure control in induction machines. I call, I think, Professor Bose to be here to start, and Professor Khabarde to just greet him with a flower bouquet. So, Professor Khabarde of Electrical Engineering, IIT Bombay, he will just offer a bouquet of flower to him.
Thank you. I welcome Professor Bose to IIT Bombay on behalf of IEEE Power Engineering Section. Okay, thank you.
Thank you, Dr. Bandyopadhyay, and good morning to all of you. Unfortunately, after 16 hours of plane trip from the United States last night, I came here at 12 o'clock, and I'm feeling to some extent sick. So I will try my best, so please bear with me, okay? And this is my first visit to Bombay IIT, And a number of years ago, I presented a paper for a Bombay IIT professor in IEEE Industry Applications Conference. I've forgotten his name. He sent me a paper. I presented that. Is it Fernandez or somebody? I don't know really. I remember these names. Okay. The title of my presentation today is Energy Scenario and Impact of Power Electronics in 21st Century. It's a very broad-based topic. No equations, no mathematics, just a broad kind of perspective on this. I am giving my email address below. In case you have questions, and time may not be enough, you can send the questions to me. It's very simple, you can remember. Please send me, because we may not have enough opportunity to have discussions here. So, in my presentation today, what I will do is, in the beginning I will give a broad scenario of the energy in the world. Everybody's talking about the energy nowadays, everywhere, everybody. So energy is a very important item. And then, in that energy scenario, I'll talk about the environmental pollution as a result of burning of fossil fuels, and what we call the global warming and the climate change problems, and then what are the consequences of that, and then how to mitigate some of these problems. Then I will start talking about the impact of power electronics in these technical part of the presentations. First, I will talk about the power electronics, the important role of energy saving, then renewable energy sources like wind generations and photovoltaic systems, talk a little bit of the smart grid, and talk about the very general, and then I will talk about a number of application examples of power electronics and motor drives area. And some of these examples I will take from my own research. And then finally I come to conclusion. Now in the conclusions I will essentially summarize what I've talked, and then in the final conclusions, two parts. In the second part I'll talk about the power electronics technology advancements, the trends, the future trends and those kind of things, Now last year I was in the University of Roorkee to give a keynote address, and some of these topics I essentially talked about there as well. Now, in the beginning, I would like to show you some publicity slides by Industry Application Society. The IEEE Society, as I said, Professor Bondavada, I'm a distinguished lecturer of the IEEE Society, and as the IEEE Society distinguished lecturer, they have paid my plane fare from the United States back and forth, and my host, the Bombay chapter, they are paying my local expenses. So therefore, the condition is that I have to give you these publicity slides. So I will go through very briefly all this information in the website, and I will not spend much time on this. So, okay, the scope of the society, basically Industrial Electronics Society, and anything related to control system applications, as it Dr. Bandyopadhyay, control systems, robotics, mechatronics, factory automation, flexible manufacturing, data acquisition, vision system, energy conversion, control management. The last one, energy conversion, which is same as power. History, then again, I will essentially skip that. Originally started with the microprocessors and those kind of things. Power electronics came quite late. Essentially, I worked for 11, 12 years, continuously promoting power electronics. And if you look in the power electronics transactions, you will see it's mostly power electronics. Organizational structure, again, all these informations are in the website, okay? So I did not spend any, but I had to show these, and I'm asking again, Mr. Bandyopadhyay, when you write your reports, please mention that Dr. Bose showed these. Otherwise, the Vice President will be angry with me. No more distinguished lecturer financing technical activities. In these technical activities, if you look, I'm trying to identify the power electronics area. There is a power electronics there, you can see. Okay, let me see this. I can see I have some problem with the eyes here. So you can see that you have electrical machines is there. Then you have motion control is there. Then you have power electronics. They're saying power electronics here, not in the broad scope. And then renewable energy systems are there. Sensors, actually smart grids has been recently added with these things. Okay, so the conference activities again, I'll not talk much about these things. Membership activities, you see, distinguished lecture program. This is IEEE Society has 15 distinguished lecturers. I am one of them. These people are very privileged people. These are lifetime appointments, and wherever I go in the world, they will finance my trips. And in fact, this year I'm visiting here, and in October I'm supposed to go to Argentina. So I'm carrying on my troubles. I'm getting a bit old, but carrying on because I enjoy these kind of things, you know. So anyway, 15 altogether. There are 50. They're all again. The website is there, and there are 50 chapters all over the world. And some places the chapters are combined with the other societies. IEEE is now a global organization. It was previously an American organization, you know, but it has captured the whole world right now. Okay, membership activities. IES publications. Publications, again, those who are doing research, they know well their industrial electronics magazine, then the industrial electronics transaction. These are the two main transactions, the important things. And you will notice one thing, a factor is called impact factor. What is happening nowadays, whenever you publish a paper in IEEE, the papers are published in IEEE Explorer, and then in a Google, there is a Scholar Google. Are you familiar with that Scholar Google? They show you the citations. These citations are very important because there are many people who are publishing hundreds of papers, but the actual value of the paper is not very good. So when your paper is cited by others, then it becomes more important. So there is a factor called citation index. Every author in the Google search, you find a citation index. That is the factor which is very important. That is the impact factor of individuals' research contributions. And IEEE awards or IEEE fellowship and all these things are now being judged by this. A fellow committee member in IEEE essentially types the name of the persons and sees what is the impact factor. So these are being more important, you know, in this communication area. Now let us come to the technical part of my presentations. Right in the beginning, before I start my power electronics, I want to open up my presentation with two important view graphs. You know, these view graphs I'm showing first two, and then I will fall back to the energy scenario and then go through step by step. Right in the beginning, what I'm saying is that computers, communications, information technology advancements have targeted geographically remote countries as close neighbors. We now live in a global society. You can see how close is this world, particularly the internet communications. The whole world is a small place, a global village, a very small village. So this is playing a very important role. Nations in the world are increasingly interdependent. In the United States, we talk most of it now, talk about India and China. Previously, old times in the television, they will show the two oxen are fighting with each other on the road, these kind of views. But now, entirely different. Now they showed India's achievements. India and China, they always, all the time, they're comparing. And of course, I'm visiting India after 4 years, actually, after the rookie, of course. But China is somewhere here, and India is somewhere here. And these are the two developing countries which are going in the front. And the United States, country like United States, they have a traditionally excellence, but they are now afraid that China need to take over them or something like that. So it's a kind of tremendous amount of images being built in the televisions on this there. So in the nations of the world are increasingly interdependent. For example, China and India, people are watching with the telescopes or whatever is happening in these two countries we're watching, and they're mutually affecting with each other. All global mutually interdependence, you know. And we are saying that the future wars will be in the economic front rather than the military front, although some wars are going on, but the future trend. And in this future war, we see the global marketplace, nations will face industrial competitiveness. Industrial competitiveness, that means which nation can produce industrial products, high quality and economical. High quality economical. So assume there is no trade barrier in the whole world. So if you can produce more, then you can export more like this, as is happening in China and Japan, or the Japanese cars. Everybody, I have 3 cars in my home, they're all Japanese cars, because those cars are high quality, somewhat economical price. American cars we don't buy anymore, though we live in America yet. In these kind of environments, we are saying the power electronics and motor drives area is a key technology for global industrialization of the 21st century. Traditionally, the European and American societies, they have already accepted widely power electronics, but it is now spreading throughout the world in other countries as well for industrial automations with the help of power electronics and motor drives area. Well, I'm showing the impact of power electronics in the 21st century. Right in the beginning, I'm opening up my presentations. What I'm saying is that 21st century will be the golden era of power electronics applications. Again, this is my viewpoint. I think we coincide with other viewpoints. I go all over the world, give presentations, and this I'm saying is that in the later part of the 20th century, it was the innovations in power electronics, most of the key research, like vector control, the space vector, the DTC control, all these major inventions in power electronics, motor drives area. And to some extent that momentum will be continued, but we are saying the 21st century will be the century for applications of power electronics. Tremendous applications of power electronics in all different sectors. And this is creating some kind of new industrial revolution, ushering in which is somewhat unprecedented in history compared to traditional old industrial revolutions. There's a new kind of industrial revolution is coming in because of the application of power electronics. To be more specific, power electronics significant roles, as you can see, exploring renewable energy sources like wind and photovoltaics, the renewable energy sources which are very power electronics intensive. They are environmentally clean, abundant in nature. That is real everywhere in the world, including India. There's some water here, having some throat. I will go a little bit easy, okay? I'm sorry for this, but so renewable energy sources is an area where almost everybody is working. In the United States, European countries, then you have China, India also. Then bulk energy storage of energy for utility systems. Because the renewable sources, they are kind of sporadic or statistical in nature. In order to compensate that, we need to have storage. And so far, utility systems requires a storage of electricity, large storage. Systematic development has not been done, but we are paying real emphasis for the bulk utility storage. Then the smart grid. I'll talk about a little bit of smart grid or intelligent grid systems, electric power grid. Research, a lot of research is going on right now. Then, of course, electric and hybrid vehicles. All these are highly intensive of power electronics. So a person working in this area has to be very knowledgeable in power electronics, electric and hybrid vehicles. Then energy conservation or energy saving or improving energy efficiency improvements. Besides the usual role of industrial automations, high efficiency energy systems. High efficiency energy systems, when we say, we mean actually, for example, HVDC systems. Then we call the flexible AC transmission system, UPS systems. These kind of energy systems we call high efficiency energy systems because they use power electronics. Power electronics is switching mode operations. Efficiency can approach 88 to 98 to 99%, so high values. We are seeing the trend of higher price of energy. In India, of course, the price of electricity is high. United States, it was very cheap. In our place, I come from Knoxville, Tennessee. It's almost one of the cheapest because the TVA, Tennessee Valley Authority area. But the price is coming up. The price is coming up, and we see almost everywhere in the world the energy price is increasing. One reason is that the sources of energy is dwindling. And the other is the environmental regulation. Most of the energy comes from the fossil fuels, and of course nuclear power as well. And fossil fuel gives a lot of pollutions. We live in a TVA area. TVA has a lot of thermal power stations, and thermal power stations, as you know, they burn a lot of coals, and coal this gives poisonous emissions, So there's a great concern, and EPA, Environmental Pollution Agency, always is trying to restrict them. As they restrict, the energy price goes up. I think it's okay. So as this happens, as the cost of energy is increasing, and we are having increasing applications of power electronics everywhere. Industrial applications, commercial, residential, transportation, aerospace, military, utility systems. The power electronics is almost spreading everywhere. When I started my career in 1960, around 1960, power electronics was a kind of very infant stage. We were not very sure about the future of power electronics. But around 1970s, I came to the United States in 1971, we find that because of the advent of devices like IGBT and power MOSFET and all these things, suddenly the power started flying. And power electronics, along with the other pulse width modulation techniques and converters and machine drives technology, it started blooming like a big fields. And now it is one of the most important fields, potential important fields. We say often the role of power electronics in this era will be as important as computers, communication, information technologies. These are already important. One difficulty with the power electronics is not visible. Often people call this enabling technology. It enables something, but public cannot see it. It's always hidden somewhere. Unlike computers and communications also. That is one very important thing here. Now let us fall back to energy scenario. Most of our fuels, energy sources right now are fossil energy fuels and nuclear, fossil and nuclear. So let me start with this idealized fossil and nuclear energy depletion curve. The resources of our energy are limited resources. This is trying to highlight here, and I'm trying to show on the horizontal axis the year, and there's the total amount of energy, and these are the resources, you know. This is a depletion curve considering the present requirements and considering the future depletion rate, and this is the natural depletion curves here. So if you look here, the coal has the maximum resources, coal maximum resources, and that is the reason. And I think in India, 73% of the energy comes from coal, and USA around 54% energy comes from coal. So coal is the primary important energy resource, kind of fossil fuels. So if we look, we are in 2012 to 2012. And then we peak somewhere here, and then gradually depletion will occur around 200 years. The typical estimate, rough estimate, 200 years. On the other hand, if you take the gas, for example, it's a natural gas, it will peak somewhere middle of the 21st century, and then it will last around 150 years. And then if you take oil, typically 100 years. Now, if you see the oil distribution curves, we are at the time of peak point, at this peak point right now. Now, that means it is now depleting. The resources are declining, but the consumption is going up, the demand is going up. The reason is that mostly we say because of China and India. The economy is booming, so therefore they need more oil. But where from the oil is coming? Oil is limited resources, and that is the reason oil price is going up. It's going up in India, I know. In the United States also is going up. Everywhere is going up. So that is one of the problems. USA, we import 70% of our oil. We have a lot of oils, but consumption of oil is very high. People have cars. Every family has one. Every person has a car. So therefore, the demand for oil is very high. So we have to import most of the oils. And of course, finally, the nuclear resource. We say the natural uranium-235 is a short 50 years intervals. Now, as you all know that the fossil fuels, that means coal, oil and gas, these fossil fuels have the problem of pollution. Pollution means different sulfur dioxide gas, nitrous oxide gas, and nowadays the carbon dioxide emission is becoming more important. It was not so before, suddenly becoming more important because the CO2 essentially causes what we call the global warming. I'll talk about more of these global warming problems or climate change problems. And the CO2, most of the CO2 comes from the burning of human fossil fuel burnings. And of course, the nuclear does not give that kind of emissions, but the nuclear has the problem of safety problems, and nuclear waste becomes radioactive for thousands of years. There's no easy solutions how to get rid of nuclear waste. In the United States, there are lots of nuclear plants. I really don't know how they would dispose West Indian cases, but they essentially put in the blocks, and locally they store it. They are supposed to store underground somewhere, but no state is agreeing to put those states here below. Okay, so the question is that these are the natural depletion curves. So what will happen, say, after 200 or 300 years when there is no fuels left? With no fuel, that means how can we run our airplanes or motor cars? Or what will happen to the human civilizations? Now, the first question is that with the conservation of energy, we can flatten these curves by conservation of energy. And also, there are possibilities that the new energy sources will be discovered. For example, offshore oils. There are a lot of offshore oil mines there, and it is said that the Arctic oceans in the north, below the Arctic Ocean, 25% of the world's oil and gas resources are hidden there. Of course, the exploration of those will be expensive, but there is possibility of exploring gas here. And of course, these curves do not include the renewable energy resources. Renewable energy resources provides almost infinity and endless resources of fuels. So that is the reason that wind and photovoltaics are so clean and so abundant. That is the reason everybody is trying to explore those things here. Then there are, of course, biofuels are there. To some extent, exploration is going on there. The prospect of fusion energy does not show much promise, fusion energy. Now, the concept of hydrogen economy is floating around. What is the meaning of hydrogen economy? The idea is that since we have a lot of wind energy, for example, wind energy sources, these wind energy, we cannot store energy to wind, so we can convert wind into electricity. And then through electricity, we can generate hydrogen by electrolysis of water. And then hydrogen can be stored. Hydrogen can be stored either in a cryogenic forms, a liquid forms, or compressed gas forms. And then use hydrogen as a fuel. Hydrogen can be used as a fuel in a fuel cell cars, or it can be used for other internal combustion engines as well. So that is a new concept. It's just a concept that is not open. Okay, as I said before, that the CO2 is called the greenhouse gas. CO2 and some other gases called the greenhouse gas. The reason is that these gases are harmful in the atmosphere. They absorb the solar heat and then preserve and raise the temperature of the world. That is the global warming problems. So a lot of studies are going on the CO2 emission in different countries and how we can solve these problems. So this is a figure showing that the CO2 emission of different countries per head in terms of tons per head and the population on these axes here. On the extreme left, you can see the United States. United States per capita energy consumption is highest in United States has a 5% of world population, and it consumes around 25% of the total energy. That is the reason the living standard in the United States is very high. Of course, the highest living standard is now in Switzerland. Okay, so anyway, as I said before, the 25% of our energy comes from the coal, and to some extent from the gas and as well. The Canada is very close here, and the European countries, these I'm showing the CO2 emission population of selected countries here. The European countries somewhere in between, and China is somewhere there. Now this is the population axis. The China is around 1.3 billion population here, and the tons per person is typically 4. You can see it's much lower than the United States. Now what is happening is this, that if you consider the total area, the area means the total emission, the per capita emissions and the population, that the total emission is given by the area. The United States being worst polluter, but the United States is what the United States is saying that they are not, United States is not agreeing to mandatory pollution controls. The reason is that they are pointing out the finger to China. Although per capita emission is low, the total emission is highest. But again, China is blaming the United States because we have created such problem now for the whole world. And we cannot restrict our fuel consumption to improve the economy, to improve the living standard of the people. So this kind of fighting is going on each other. Now, Brazil is a very interesting country. You can see its per capita emission is small, but it's a very good living standard. There are several special things in Brazil. Brazil, 95% of the energy comes from hydroelectric. It's very clean. And then Brazil has an Amazon rainforest. Amazon rainforest, you know that trees, they absorb carbon dioxide. So they clean up the atmosphere. And also, they are 50%, more than 50% of the oils is from biofuels, from sugarcane ethanol. So which is somewhat environmentally clean. So this is, and very recently Brazil has a booming economy because they have a lot of offshore oils there. And India is somewhere here. India's population I think is 1.1, somewhat less than China, and its per capita emission is somewhat less than China, almost half of the China. So this is essentially the picture which is important for environmental pollutions. Now let us talk about the climate change problems due to greenhouse gases. Now, Earth's atmosphere accumulates solar heat and raises temperature, which we call the greenhouse effect. Now, solar heat which is coming on the Earth, it is being absorbed, and this is absorbed by the greenhouse gases. The reason we call it greenhouse gases is that it absorbs the solar heat and it raises the temperature. And this is a few degrees in 100 years, we call it greenhouse effect on gases here. And consequences of the greenhouse effect is disastrous. You know, I can show you what is called the melting of glaciers or polar ice caps causing inundation of low-lying areas. It is already happening. When I'm coming by the plane on the high, I can see the Arctic Ocean. Arctic Ocean freezes in the winter, but in the summertime it almost melts. Now, the tendency for melting is more and more because of the global warming, temperature rise. And as it is happening, the more and more inundations of the low-lying lands. The United Nations estimated that around 300 million population is within 3 feet of water. So eventually there will be submerged and displaced people. And there are a lot of glaciers around the world that is also melting, those are melting. A lot of research is going on right now, a lot of research in the United States, in other countries. There are climate scientists that are doing research on these climate changes. Supercomputers are being used, and they are trying to model the whole climate systems, which is extremely complicated, and then study in computers and then try to predict the temperature rise and the consequences here. Now, what are the other adverse effects on the climate change? Severe droughts on tropical countries near equator. As the temperature rises, you have droughts, and then rise near the equator. For example, India and Africa, these are the countries which will be affected most. In fact, recently there was a global warming conference in South Africa. African countries are demanding money, billions of dollars from European and American countries, because they are the people who are creating this global warming, and African countries will be suffering as a result, so they are asking for compensations of this. Damage to agriculture and vegetations because of the heating effects. Then hurricane, tornadoes, heavy rains and floods is already occurring. Spread of diseases. Some animal species like polar bears and penguins and corals, they tend to extinct from the earth because of the global warming. The corals, if you have not gone, I've seen the corals in Great Barrier Reef in Australia and eastern side of Australia. That is the global center for corals. And what is happening? They're very temperature sensitive. As the temperature is going up a little bit, the corals are dying in massive scale. And also the acidity of the water. What is happening? The carbon dioxide in the air that is being washed by the rain and forming carbonic acid, very weak acid, falling on the water. That acidity is also affecting on the marine life, including the corals. So a lot of these are not very clearly known. So a lot of studies, scientific research is going on right now for these effects here. Now, these are some of the example scenarios due to climate change, and these are the things which are estimated by the United Nations figures. Now, all these informations are available in the internets. They said that 50% of Bangladesh will be underwater in 300 years, displacing 75 million people. Bangladesh is a very low-lying land, so inundation will be much higher. I come from Bangladesh, I can see it's very flat and low levels. So some island nations in the Pacific will be underwater. Pacific nations have small lands, being underwater. They are applying for the help from the United Nations, And so these preparations are going on. This is one important factor. India's agricultural productions will decrease 38% by 2080s due to droughts, but CO2 fertilization will offset by 9%. This is very important. The droughts will cause a decrease in the agriculture, but at the same time, the CO2, which trees like, absorbs CO2 and gives a growth, so like a fertilizer. So that is an effect. Now, these are again by the United Nations. I'm not sure. I'm sure the government of India and people are aware of these kind of problems. If Antarctica and Greenland ice melt, now Antarctica, Greenland, they're full of ice. And if these ice melts eventually, the ocean level will rise by 200 feet. So you can see how much land it will cover these things. If all ice in the world melts, the ocean level will rise by 210 feet. Even the New York will be underwater, Manhattan will be underwater at this kind of water levels. Arctic regions, as I said, Arctic regions, Arctic Ocean is already, most of the ice and waters already, and it will be virtually free from ice by 2070 and things. But again, this study has told that if the fossil fuel burning is completely stopped today, the ocean level will rise by 4.6 feet in 1,000 years. So even if, theoretically, if we stop all the fossil fuel burnings, it will gradually rise and then slowly go down, you know. So that is because these CO2 and these greenhouse gases are not only given by the man-made burning of the fossil fuels, but there are natural ways from coal mines, coming from the underground waters and volcanoes and all these things. So this is the kind of very vital. So a lot of research going on in these kind of areas. You know, we said that the countries near the equator will suffer most, you know. Now the question is that how to solve and mitigate the global warming, or climate change problems. Now there is a treaty called the Kyoto Treaty, 1997. It is the United Nations treaty which was signed by member nations agreeing to decrease the pollutions. So it is not really working right now. It's a kind of, the European nations, they are the pioneers for this Kyoto Treaty. United Nations is a member, but United Nations, there are a lot of divisions, opinions, because the oil and gas are very important in the United States, so those are companies, they are highly resisting these things, but then you have a EPA, Environmental Protection Agency, or the government, they are fighting, so a lot of fighting is going on. So it's a kind of voluntary, right now it's a kind of voluntary reductions here. So the question is that how can we solve and mitigate climate change problems? One thing is that promote all the energy in the electrical forms. And when you do that, you can burn fossil fuels, but you centralize all fossil fuel burning in the electric power generations and apply advanced emission control techniques. When you're burning these fuels, you apply emission control techniques right in the power stations. You know, it's much easier than the distributed burning of the fossil fuels. Okay, then cut down or eliminate coals. So coal is the culprit for all pollutions. And this is not very easy again because the coal is the major fuel source in most of the countries. But again, the coal power stations, the efficiency is quite small, and a kind of research is going on, what we call the clean coal technology. How can we clean the coal? One is, of course, as the coal is burning, this CO2, which is a bulk CO2, absorb this CO2 and then carry in a remote place and then put it in underground. They are trying all different kinds. There is another called IGCC process. That means they convert coal, gasification of coal, and then isolate the CO2. These are very expensive processes. You know, coal energy, electricity from coal is cheap. But if you try to clean the coals, the pollutant gases from the coal, then it becomes very expensive. So it's very uneconomical again. So the trend is maybe one day the coal will be completely eliminated as a fuel. Then increase nuclear power. But as I said, the nuclear power has its own problems. So recently there was Japan nuclear reactor damage. We are familiar with the nuclear reactor meltdown, Fukushima in Japan. So as a result of that, that has created a lot of adverse effects. In the United States, we are in a kind of halt mode. They are now checking out the safety of the nuclear power plants. Germany has declared that they will abolish the nuclear power in 10 years. So a lot of adverse effects on nuclear powers. Then preserve rainforest and promote widespread forestations. Because the trees, they absorb CO2, so why not have more forest like Amazon rainforest? so they will absorb more CO2. Control of human animal population, that's not very easy. The human population, for example, we exhale carbon dioxide, and also more population in the world means more requirement of more energy, and more energy means more fossil fuel burning, and same thing with animals. So that is not very easy solutions. They promote usage of renewable energy sources. That is the reason wind, solar, geothermal, biofuels, fuel cells. So that is the reason renewable energy sources, as I said, are cheap and abundant. So that is the exploration is going on, the reason here. And replace ICE vehicles by electric vehicles. That is also electric vehicles. A lot of R&D and a lot of products are coming up nowadays, electric vehicles here. And promote mass electric transportations. Mass electric transportations means less pollutions, instead of driving individual cars. One of the problems in the United States is that everybody has a car, and this car gives a kind of pollutions problems here. And of course, save energy by more efficient generation, transmission, distribution, utilization of electricity. That is the attempt is going on in the smart grid, which I'll talk a little bit on later. Then all the whole grid system, the generation, transmission, distribution, all these, typically these systems, they're around 6 to 8% of electricity is lost here. And utilization, of course, including utilizations. So with the help of smart grid or the intelligent grids, we can reduce the energy losses in the systems, the power systems. And of course, to prevent energy waste, as the waste of energy is a very important factor. United States particularly, typically we say that 1/3 of the total energy is simply wasted. One reason of waste is that the energy is cheap, and people tend to waste energy because they have a bad habit of wasting energies. A lot of affluent people, their big houses, and heating up those houses, simply a lot of energy is simply wasted here. So these wastage of energy, we discourage these wastage of energy. That will be very helpful. And now all these last 4 items, you can see, 4 items, they are power electronics intensive. We'll come back to those later on. Now let us fall back to power electronics and energy saving. The tremendous amount of effort is now being paid with the saving of energy with the help of power electronics in the United States and other countries as well. So let me talk step by step. It's very important here. Now, you all know that the power electronics is conversion and control by electronic switching of highly efficient than traditional rheostatic control and MG set of controls. When we were students, we used to use a lot of MG sets, motor generator sets and all those things, but those days is gone now. Rheostatic control is still many places, in subway drives or metro drives, even they use the rheostatic control of DC motor drives. That's very wasteful, but instead of rheostatic controls, if you use chopper controls or inverter controls with the help of power electronics, then the efficiency goes very high. So you can save a lot of energy like this. Then the another important factor is that 60% of the grid energy in the United States, I'm giving an example in the United States, used in machine drives, mainly for fluid flow control by pumps and fans. Pumps and fans which flow control, flow of air or flow of oil, and those fluids, that controlling of that flow, 60% of the used. And of these, around 75% of these are industrial applications. And the traditional methods of controlling these fluid flow is that there is an induction motor running at a constant speed, and then the flow control, they put some kind of nozzles or restrictors, so called a damper throttle, in order to control the flow. So that is very energy wasteful, because that as the air or the fluid goes along, it creates a lot of vortex. On the other hand, if you have a fully open throttle and run the induction motor at variable speed, so the flow is variable directly, so that gives you much efficiency improvements, So gradually it's coming up, these things. The additional cost requires the power electronics to have a variable speed drives, but the additional cost, if you're saving energy, you're saving money, you will recover the cost within a reasonable time, particularly where the energy is more expensive. As you know, possibly in Japan, the energy cost is very high, and they are very efficient in using power electronics for energy savings, unlike the United States, of course. So the cost, where the cost of energy is high, they are using power electronics for saving energy is much more incentive there. And in addition to that, if you are running, normally machines are run at a fixed flux, rated flux in a variable speed drives. If you control the flux, that means as the machine speed is going down, lower speed, use a lower flux at the light load flux weakening, you gain efficiency improvement as well. So therefore, this requires a power electronics for controlling the flux. So this is showing also that you can improve the efficiency by programming the flux. Okay, then variable speed load proportional air conditioners. Normally air conditioners, they run operated with the thermostat controls, on and off thermostats, which has inefficiency. On the other hand, if you have a continuous flow controls, that means your requirement of cooling is going up, run the compressor and the speed is so higher, and then reduce it as it demand requirement goes down. So this is called the load proportional controls. You can save a lot of energy. In Japan, they use a lot. They use load proportional variable speed drives for the air conditioners. In the United States, we don't use much of this because, again, the United States, the energy is very cheap. That is the reason we don't use that much here. Then in the lighting controls, again, 20% of the grid energy is used in lighting here. And here, as you all know, that the compact fluorescent lamps are much more efficient than incandescent lamps, 4 times more efficient and 10 times longer life than the incandescent lamps. And now we are in an era of emerging solid-state LED lamps. I don't know whether you got LED lamps in India or not. They are now flooding the US markets are coming up. They're expensive, quite expensive. But LED lamps, they are again requires a lot of power electronics. 8 times more efficient and 50 times longer. I have some LED lamps in my home. They are very low power. LED lamps, you cannot buy high power, so low power. Then again, you can number of them. You can make it high power, but it's again becomes too expensive. Its price is coming down here. Then, in addition to these, we call the energy systems, such as the flexible AC transmission system, HVDC, a static VAR compensator, uninterruptible power supplies, active harmonic filters. These are all in the smart grid can improve generation, transmission, distribution efficiency. As I told you before, that the smart grid, or we call intelligent grid system, where you can do a lot of actions, a lot of activities in such a way in order to reduce the losses of energy in the systems, And then you have electric transportations, again, like electric vehicles. Ship propulsion can save a lot of energy. Nowadays, propulsion ships, the big ships, they normally run by diesel turbines. Now the train needs diesel electric generators, and then use the variable speed drives. In this way, you can save a lot of fuels, and there's a lot of advantages. So most of the cruise ships, I know they're all power electronic variable speed drives. Even the drives in the systems, the ship propulsions in the military ships also, they are being electrified now. Now the wind energy scenario, coming to the wind energy scenario, as I said, wind energy, it is most economical, is renewable energy. It is environmentally clean, unlike coal and gas. We call it green energy, and the cost is typically 7 cents per hour. So we have a wind turbines. Wind turbines can be either on the land or it can be offshore, on the ocean, on the water, And these generate energy, and the energy generation depends on where is the land or the pattern of the wind. Sometimes there's no wind, there's no energy, so it's a utilization factor. We call it utilization factor that determines the cost. But the world has abundant wind energy resources. The European Wind Energy Association has estimated that even the 10% of the available economical winds of the whole world is enough. 10% exploration is a whole to supply all the energy needs of the whole world, And recently there has been a lot of technology advances in power electronics, variable speed drives, and variable speed wind turbines. And I know in India and China, these countries, a lot of application of wind energy is going on here. It's very cheap. It is competitive cost with the fossil fuel. Like coal energy is typically 6 cents per kilowatt hour compared to high. But again, as I said, the United States, now the problem is occurring of the pollution control of the coal plants. Government is putting a lot of restrictions of the coal emission from the coal-fired coal plants, and as a result, the price of the coal energy is going up again. We live in the coal area. Actually, TVA, we have a lot of hydroelectric dams in our place, as well as a lot of coal stations. Coal power stations, they're producing a lot of CO2. Of course, is not damaging, but they put sulfur dioxides, They put mercury and all these things. So government is putting a lot of regulations to control these things, you know. Okay, completely cost of the fossil fuel powers. If you put wind stations offshore, the recent trend is to put wind generation offshore wind plants. That means on the ocean, and on the ocean there's a lot of winds, you know, so you can extract more of energy from the winds if you put a plant, wind generation plant offshore. But the problem is that if it is remote from the central grid or central load centers, then it's more expensive to carry those wind energy and tie to the grid. So this called, I said, the remote offshore wind park. Normally they are connected by high voltage DC grid interconnections. They can be more expensive, like $1 million per miles. In Texas, in the United States, for example, is an area where a lot of wind energy exploration is going on. And recently there was a private billionaire, T. Ben Pickle name. He had a lot of private business for the wind generations. And then when he found the wind generation is cheap, but when you need a transmission lines to continue, it becomes more expensive. Then he went out from the business, sold all his wind turbines. This is all these factors you take into considerations. Okay, currently United States, the world leader in installed capacity and total energy generations. Now, actually, what has happened that in terms of the total wind energy generations, China has taken over the United States. China is now #1 in terms of total. I don't have any figure for India actually, but I know India has a lot of emphasis going for wind generations here. Okay, now currently about 3% of wind energy is generated in the United States, and there is now a lot of installations going on wind energy. So we have a goal of using 20% by 2030. Denmark is a country which is the leader in terms of total percentage use. So they have 20% wind energy, and it is in the vicinity of the North Sea. North Sea has a strong winds there, and there are many wind turbines, in the North Sea. I have myself seen those wind, they call offshore wind park. It's very interesting. Big, large-sized turbines are moving very high speed all the times. But Denmark has the ambitious goal of 40% by 2030. One of the problems of the wind energy is that it is statistical. That means when there is a wind, there is energy, and when there is no wind, there is no energy. So it's very unlike your thermal power stations and nuclear power stations. It's very sporadic in nature. That is one reason for which you need to have storage. When you have a surplus energy, you can store it. And then when you use that storage energy. So that is the reason with the growth of the wind energy, or also photovoltaic energy, you need more storage here. So this we call the wind energy, the key energy source of future hydrogen economy. We are thinking about the future hydrogen economy. No pollution, it's clean, all energy is coming from hydrogen gas. And the other idea is the abundant wind energy, or also the photovoltaic energy converted to the wind to produce this. Now this is a figure showing the fuel cell fuel cell car. Here is a fuel cell. The proton exchange PEMFC is the usual fuel cell for the car, and use that as like a generating electricity generators. Use that electricity, and because the fuel cell is a low voltage device, so you need to have a DC-DC converter, and then that DC, it goes through an inverter and generates variable frequency power supply for the motor. Now, the fuel cell cannot regenerate when you have a braking from the car. The energy is flowing in the reverse directions to the inverter, but the fuel cell cannot recover that energy. So you need to have an auxiliary storage, which is put here, ultra capacitor or a battery here. You need another DC-DC converter there in order to do that. Now, on the left-hand side is showing the resources here. The fuel cell here, the hydrogen is burns with oxygen. So oxygen is easy, the air from the air, compressor air, compressed air. But hydrogen is normally we are talking about using water and using wind energy. So here as the wind energy, wind turbines here, and here is the wind generators, and use electrolysis of that to generate hydrogen, and then use that in the fuel cell. So that is the basic concept. Of course, you can use the electricity from the water in the electrolyzer, Or the other ways, of course, you can use the photovoltaic and nuclear, but the wind is the cheapest, as I said, the cheapest abundant source, which you can easily use to generate the hydrogen. So, and on the dotted line, I've said all these ideas are going around. The hydrogen can also be generated from the coal gasifications. Use the coal, pulverize the coal, get the steam, then you generate hydrogen from there. It's more expensive than the other methods. And then it produces CO2. That CO2 you put underground storage. The idea is put underground. There's a lot of caverns, a lot of salt mines and caverns here. So pump it in the underground and then use that hydrogen from the fuel cell. There's ideas in there. But the most common idea is from the wind turbines here. So the fuel cell car is another area where a lot of research is going on in the recent years to replace the IC engine cars. Now here comes the photovoltaics. You're all familiar with the photovoltaics, generation of electricity from the sunlight. It is also static, it is safe, it is reliable, it is environmentally clean, just like wind energy. One particular importance of the photovoltaic is that it does not require repair and maintenance. There's no moving parts, everything is static in the photovoltaic energies. But unfortunately, PV panels are expensive. Photovoltaic panels are expensive, typically around $2 per watt or 30 cents per kilowatt hour. And the price is falling fast due to recent technology advancements. A lot of government incentives going on for generation of cheap photovoltaic cells, PV cells. I say $2 per watt, but most recently there is a company in California, they are putting up 74 cents per watt. But again, these are just started here. Some companies are starting, some companies are failing. So we are expecting that very soon, very recently, we will having a very economical photovoltaic cells for power generations here, technology advancements. And again, photovoltaics remains very sporadic nature of power. In the daytime, you have power. In the nighttime, no power. Or in a cloud on the sky, no power. So it's a kind of fluctuating kind of energy source. It's much better to have storage as a backing to store the surplus energy. The PV cells have been used, the PV space power stations, the space satellites that we use a lot. The rooftop installations, particularly in Japan. Japan, the energy cost is very high. They do not have oil and gas or coal, so the energy cost is quite high for Japan. So they have a lot of incentive for using a PV, photovoltaics here. So rooftop, we are expecting in future also most of our homes will have PV panels on the rooftop installations, kind of local energy, free energy, not dependent on utility grids. And then of course there can be PV stations, either remote installations, off-grid or grid connected. Grid or off-grid connected. Now off-grid is very important. Both photovoltaics and wind energy is a very big source of energy for off-grid installations. It is said that around 1/3 of the world populations here, many countries, there are a lot of people are in the off-grid. In the off-grid, wind and PV are a very important source to them. So you can generate energy, and then you can use a backup battery storage when there is no wind and there is no light for the solar energy from the battery. So this kind of off-grid or autonomous systems, there are a lot of the systems even in the United States. There are a lot of remote areas where there's no electricity, no grid energy is available. And particularly for developing countries, very important. Now here is one important statement here. Scientific American paper from the Stanford University predicts the renewable energy alone with the storage can supply all the energy needs of the world. So there is so much of renewable energy all over the world, particularly as I say, the photovoltaics and wind. There are of course geothermal, there is wave energy, tide energy, and of course hydroelectric power is also renewable energy. So all these renewable energy, that means we can completely get rid of the fossil fuels and nuclear power plants. Nuclear power plants, I said, there's a lot of controversy about the safety points of view, and coal is controversial again because of the pollution problems. So we have so much of renewable energy sources. These alone can supply all the energy needs of the whole world. Now here I must also mention that in North Africa there's a Sahara deserts, and Kalahari Desert is southern side. European Grid has a very ambitious projects there. In Sahara, for example, they put all photovoltaic areas here, photovoltaics. huge amount of solar energy and then collect this energy and the high voltage DC grid connect to the European grid system, because Sahara is very close to Europe. So these kind of ambitious plans for future, they require a lot of capital installations. Right now the condition in Europe is not that good. So they have this kind of future, similar kind of schemes can benefit a lot of India as well. There is another area of electric and hybrid vehicles, all over the world, particularly the United States, Japan, Europe. I don't know much of India. There's a lot of electric vehicles. And historically, for many years, the EV projects are going on. The main motivations for EV is, as you know, there is the petroleum fuel rise. The rise of price of gasoline is one of the main, and the pollution. The urban pollution is, of course, the more important points to get rid of the. In USA, tremendous emphasis is going on for the electric vehicles because, as I said, we import 70% of our fuel and mostly are used for automobile transportations. So if you can get rid of these, it can save our foreign exchange and also clean up the environment as the main. Now, electric vehicles, I came to work in General Electric Company in 1976, and when I came there from the RPI, Transfer Institute, I worked for GE Research Laboratory for 11 years, and most of the time I was doing projects with electric vehicles. The Department of Energy is giving big money to GE to explore all kinds of electric vehicles, the hybrid vehicles, electric vehicles. In those days, the battery, the lead acid battery was main thing, but we found, I'll talk about that a little later, okay? The electric and hybrid vehicles, they are essentially power electronic intensive, but as a technology, this is much well-developed technology in power electronics. The main problem in the electric and hybrid vehicle is the battery technology. Tremendous amount of research has gone for many years. We used to use a lead acid battery, but we found it is too heavy and there are a lot of problems. The limitation of the battery technology is one of the problems. Electric vehicle has not been accepted so much. The cost of the battery is high. The cycle life of it is high. The size is big, weight is big, and there's a fast charging problem. These are the problems here. Now, the battery technology has gone through evolutions. Originally it was lead acid batteries, and then right now it is nickel metal hydride, and then now has settled down as lithium-ion batteries. This appears to be the most important battery for now and future. Lithium-ion based battery is the future, but it's expensive again. The cost of the battery is very important. So it's going down gradually. The intensive research, as the research is progressing and the more applications, the price goes down here. Well, we expect that as the battery technology matures, so all electric hybrid vehicles now solely centers on the battery technology. Can we get the cheap battery with a lot of energy storage, so it is lighter, more cycle life and all these things? But eventually when the battery becomes mature technology, then we expect that the hybrid energy, HEV, hybrid electric vehicles, which is essentially the combinations of the battery, electric and IC engine, they will eventually go away. Ultimately, all electric cars here in future. Then the utility distribution system overloading problems with the mass use of electricity is another area which is bothering. If you have everybody is in electric car, they're charging their battery from the same battery from the household distribution system is loaded tremendously. So whether the distribution system can have also heavy load. But now the new smart grid technology is coming out where they're saying that dispersed charging base in the night time and off time will give you cheaper rate. And when there's a lot of off-peak grid energy is available, so this is what we call under the scope smart grid, which is coming up nowadays. So off-peak charging electric vehicles. Now, just I wanted to mention a few on the market. As you possibly know, Toyota Prius, so HEV, we call the non-plug-in hybrid vehicles are very popular in the United States. A lot of people have these, my colleagues have these. And non-plug-in vehicle means non-plug-in plus plug-in. There's a two classes. Non-plug-in means it has a hybrid vehicle as a battery. This battery, you're not charging from the source, you're charging from the engine. So it is a small battery. And this small battery, you're charging from the engine on the car, the HEV. And this Toyota Prius, you cannot run in a pure EV mode. The battery, most of the purpose of the battery is to absorb the regenerative energy. When you're braking the car, it charges the battery, so that gives you the efficiency. And also it aids you when you're climbing the hills or trying to accelerate. So this is a kind of, but when you come to the plug-in versions, the Toyota soon will come to plug-in versions. In a plug-in version, the battery is somewhat bigger. That means it's more expensive, but you have an electric vehicle mode. You are driving in a city, you can run as a pure electric cars, no pollutions. Or you are driving in highway, you can combine electric and hybrid both together. So right now, Toyota prices is nickel metal hydride, but every day they sell, soon they will be introducing lithium-ion based plug-in type of hybrid vehicles. Now there are two cars which are coming up and introduced in the US market. We call it Nissan Leaf. This is a pure EV, lithium-ion battery, 100-mile range, and the Chevy Volt. This is I've also given you the prices here. Now sometimes the government gives us an extra kind of incentive price to buy a little bit cheaper price, for more applications there. Chevy Volt is General Motors, and Nissan is a Japanese company. Now Chevy Volt, they are just introduced very recently. Recently in the crash testing, the battery got fired. The lithium-ion battery is one problem. They get overheated, and in worst case fires and causes safety problems. So it has just stopped into the market, the General Motors, Chevy Volt, the General Motors kind of things. There is another electric car called Tesla Roadster. The price is $100,000. It's a pure lithium-ion, pure EV, 300 miles range. Only $100,000, only the movie stars, very rich people can buy this. They're very limited market, but it is very precious and toys here. There is an ambitious prediction that 90% of automobiles will be electric by the end of this century. We need electric cars, no doubt, because there's so much of shortage of gasoline price, market price rise, pollution controls by regulations, and so the technology is coming up. A lot of research in lithium-ion batteries. In the United States, our government has put a lot of money in lithium-ion battery research. So we are expecting that in future, gradually transition to all electric by the end of the century, 90% of them electric. So we are essentially approaching there. The battery research is very complicated, and it is not power electronics people. These are chemical engineering department. In the University of Tennessee, there's a chemical engineering department. They have a cell for battery research. So it is all the electrochemistry kind of things, Okay, here is an interesting slide here. Comparison of battery electric vehicle to fuel cell EV. I told you before that a lot of research is going on the fuel cell electric car and the battery electric cars. So the question is, which one is better? Where do they stand? So here is the kind of comparison. So this is a slide I'm showing you. This was published by Arizona State University, and it was a government-funded project, like an active comparison between the two. So on the top, it is showing that the battery electric cars, and in both cases, it is assuming that our energy is coming from the wind energy. The energy normally comes from the fossil fuel or nuclear power generations, but this is a kind of futuristic kind of, where we are assuming that all our energy is being generated from the wind and photovoltaic, some renewable energy source. Now, if you look very carefully on the battery EV on the top, wind energy and then the power line, I put some efficiency figures, the battery charger, then lithium-ion battery, efficiency, where you are in the timing source. Running quite late actually. Okay, then you have lithium-ion batteries. It means I'm still very early actually. Okay, so we have electric drivetrain here. So this portion is the battery EV, and it is showing in both cases you have a 135 horsepower. The total range in either case is 300 miles. And on the top I have given you some efficiency figures. If you calculate the total efficiency, so that means if you have a 60 kilowatt hour on the wheels, you need to generate around 68% efficiency. Total efficiency generation 68%. If you go to the fuel cell electric vehicle, make kind of comparison, assume also that the energy is generated from the wind energy, then first you have electrolysis and then generate hydrogen through the hydrogen gas pipelines. Then you have a fuel cell where you burn the fuel cells in the fuel cell, generate electricity, and then turn the drivetrains and goes to the wheels. In both cases, you can see that 135 horsepower is required and 60 kilowatt hour goes to the wheels. And here also I put the efficiency figures. If you combine these two and compare, the energy efficiency for the electric car, battery electric, is 68%. On the other hand, for fuel cell is only 30%. because these are multiple conversions of the energy, so efficiency is quite small. And also if you consider the 38% less efficiency in this case, and 43% more weight for the fuel cell vehicle, and the cost is 50% more. So the objective is, you can see the realistic comparisons. Again, it's a little bit futuristic, you know. It shows that the fuel cell car cannot stand in front of the battery cars. Battery electric vehicle is much more superior than the fuel cell vehicles. And as a result of this evaluation, in all cases it is superior, the battery electric vehicles. As a result of these, the fuel cell cars, the project has been backed down. Fuel cell cars backed down. In fact, the General Motors is a company which is doing a lot of research on the fuel cell, not doing any more for fuel cell for car. You know, fuel cell is important for other installations as the auxiliary energy source, for UPS systems and other applications. But for the car, I'm talking about the fuel cell car is not very viable compared to the battery electric car. So this is a kind of important slide here. Let us talk a few words about the bulk energy storage. It's very important right now for the electric vehicles. We need energy storage, but that is a small energy. But here we are talking about the utility system, bulk energy. In utility systems, particularly when you have the renewable energy systems which are kind of fluctuating source, when you have a surplus energy you need to store, and then when you have more demand you like to feed it back. So that is the reason much effort is now being put on the bulk energy storage. Now these are the different types of energy storage. We call it pump storage in a hydroelectric plant. Here basically conversions of electricity into potential mechanical energy. And there's other is called the battery storage energy. I'll give you some actual practical installation examples. Then of course the flywheel energy storage. Then you have ultracapacitor storage. Then superconducting magnet energy storage. And V2G, called the vehicle to grid storage, is a kind of new concept. What the idea is of V2G is that vehicle to grid, if you have lots of people using electric vehicle and they have this vehicle charger is connected to the grid, then the grid can use those local small batteries as energy storage, and then that energy can be recovered as needed. So we call it V2G. Then hydrogen gas storage, and then compressed air energy storage. Now hydrogen gas, I already explained the abundant amount of wind energy convert into hydrogen and store it. So that is very easy to understand. Battery storage has been traditionally used, but these are very expensive. A lot of research is going on in battery storage. There are a lot of some plants are there. You can see lead acid is a traditional source. Lithium ion is very expensive. NiCad, sodium sulfur. A flow battery is a kind of new battery called a vanadium redox battery. Is a kind of new battery has come up for bulk storage, and there are some installations of these. I went to Fairbanks, Alaska, and found they have the world's largest energy storage. They use NiCad battery for energy storage. These are expensive, you know, but in some cases you need to have storage, although it's expensive. The price-wise, the pump storage is the cheapest if you have a favorable plant available. Pump storage, you understand the pump storage, what they call in the daytime or in peak time, you generate electricity by the water. And then in the off-peak time, take the tailwater and run generator as a pump and store in the head. And then, so this kind of generator to motoring kind of reversal of energy, that may be cheap, depending if the favorable side is there. Now let me take an example of the example of variable speed pump storage in a drive. In Japan, they have a installation they call Kansai Power Company installation, the world's largest. They call it variable speed generator pump storage. Now, in the daytime, they run as a generators. You know, this is, you can see the water from the turbine, the Francis turbines, and the turbines, and they generate electricity by the Scherbius drive. This is called a variable speed or sleep energy recovery drives here. Now, in a hydroelectric plant, there are a lot of technology behind this. In a hydroelectric plant, typically the head water varies. And they found instead of using a fixed constant speed synchronous generators, if you use a variable speed generators, you can have a more energy generations, more efficient energy generations. So they are using as a variable speed generator, this is the world's largest, the 400 megawatt, 400 megawatt sleep energy recovery drives. So it's a variable speed drives for generation. Now when it acts as a pump, water is being pumped from the tail to the head. It also runs as a synchronous motor, or not synchronous motor, variable speed motor. As a variable speed, efficiency is higher. So this is the sleep energy recovery. I hope you are familiar with the sleep energy recovery, which is very common in the wind generation system. This kind of drive system is used a lot. But this is very high capacity. You can see sleep energy from the sleep rings goes through a cycloconverter. It's a 72 MVA, very high power. And then it runs at a subsynchronous speed as well as supersynchronous speed, and the sleep power can flow in either direction, so this way or that way. So this is the example, actually, Japan's example, and this is the only example we have in the whole world, variable speed hydro. This is a variable speed hydro as well as the pump as well. Now here is an example, what we call the battery storage. Battery storage, lead acid battery storage. This is an example of installations in a Southern California Edison grid by General Electric Company. See, here, basically the storage of energy in a lead acid battery is a bulk. These are a little bit old plants. As you know, today you try to install this plant, you will not use the same kind of power. The power conversion technology has gone through tremendous amount of progress, you know. So, but this is the standard, this is the existing installations I'm showing here. On the left-hand side, you have a lead acid batteries. On the right side of the grid. So in the off-peak times, what you saw electricity from the grid, you convert these to DC, DC, and charge the batteries. And in the peak time, storage battery flows to the grid. And this is called the 18-step converter with a phase shift control. Now, if you look very carefully, they are GTO type of devices. Now, GTO devices right now obsolete. Nobody should design any equipment with GTOs. But at one time, the high power device, the GTO, were very important. So this is a phase shift control. On the top, there are 3 H bridges. So there are 3 units. And on H bridges by phase shift control, you can generate a variable voltage. And then through a transformer coupling, this is one top H bridge. This is give you 6-step waveform. Then by phase shift control, 6 step, 6 step, 6 step, you can generate an 8-step converter, and through a transformer coupling through secondaries, you can generate a 18-step waveform into the grid. We are avoiding PWM. Normally nowadays, of course, the PWM, but because the GTO is a high switching loss, so pulse width modulation is not a good idea. So it's a 6-step waveforms, which has a 60 Hz switching frequency. And they have, of course, the regenerative snubbers and all those things. And the transformer is quite bulky, it's a 60 Hz transformers. So this helps to couple and boost the voltage, and then of course you have a filter there from 18 step. You can filter the higher harmonics and then connect it to the grids. So energy can flow in either directions, and of course when you are not having energy flow, the whole you can disconnect from the battery and then use the whole system as static power compensators or StatCom. You can have a control of the reactive power from the utility side, both positive and negative, plus Q or minus Q, controllable. You can use it. So multiple purpose operations of these. These are phase shift control, again, as I was saying, instead of the pulse width modulation controls. So this is kind of Southern California Edison grid. This was developed by General Electric Company and a number of years ago. These are existing installations here. Now let us talk a few talks about the smart grid. Nowadays it's a very hot topic. People are talking about always about the smart grid. The problem with we have traditional grid systems, traditional existing old grid systems, where you have a lot of generation of powers, a lot of distribution of the powers and consumption of the powers. And a smart grid is to call it advanced grid, and let us see how it makes advancement with existing grids here. Now, first thing is the smart grid we call it is advanced power grid of tomorrow with the state-of-the-art power electronics, computers, and communication technologies. And with the smart grid, you gradually transition to carbon-free society, gradually in the future. So the modification of the grid is not very simple because you have an existing, very expensive installations. So you have to develop the technology and do step by step. Now, what is the objective of this smart grid? Objective of the smart grid is that optimum resource utilization. So you have the generators, generators, some are bulk generators, some are distributed renewable energy sources, and economical electricity to the customers, then efficiency has high in the systems, the higher reliability of the system, higher security of the system of the energies. And in smart grid, we have a lot of distributed energy sources, then lots of bulk storages. One of the most important elements of the smart grid is supply-demand interactive energy management. This I'm going to talk a little bit about this. As I said, in a grid systems, generation follows the demand of power. You have a load as your power is being demanded from the grid, generator is supplying this grid. So as a result, there is what we call the peak time and off-peak time. So when there is no demand here, in the night time, for example, a lot of generation systems remaining idle. So, and also the lot of distributed energy, renewable energy systems also in the same situations here. So here the objective is it possible to modify the demand curve and to make it suitable so that the generation follows the demands. So what you can do, a lot of consumers' demands like washer, dryers, and these kind of things, or charging of the electric vehicle batteries, all these things, you can ask them to charge in night time. In the night time, when there are a lot of surplus grid energy available, you can offer a cheap electricity and ask them to use it. So this is possible, what we call the smart meters. Smart meters will essentially sample these requirements and then force the charging in the off-peak times, and the consumers are benefiting by the economical price in the city. So this is much economical than in the traditional grid system. So here the demand actually follows the supply. So that is the most important things here. And also, in addition to these, in a grid system, when there is a demand of power in one place, a computer and communication technology, all things can calculate which generator should supply what power and which route it should follow. In that way, the utilization of the resources is optimum, as well as the losses in the transmission is also minimum. So this all can be computed and planned properly. So this is what we call the advanced grid of tomorrow. So a lot of work is going on right now in the United States, in other countries as well, for what we call the typical name is the smart grid. Here is an example installations of what we call the off-peak wind generation systems, offshore wind generation systems. Now what is happening is that on the left-hand side is an offshore wind park. That means a lot of wind generation systems are being combined together. So the power is coming here, this is an AC power, and then with the HVDC grid, the power is flowing to the other side to the receiving stations. And these I'm showing an example of actual installations. We call ABB HVDC light. This is in the world's largest offshore wind park interconnection to the German grid. So the total capacity is 400 megawatt, 150 kV, 400 kilometer cable length. So again, I'm repeating here, on the left hand side, you have the offshore wind park. Actually, it is a wind park on the North Sea. So this power is coming through a transformer, is an on-load tap changing transformer, 3 winding transformers, and that is coming here to a converter stations. And these converter stations, this is actually a double-sided 3-phase PWM IGBT converters. I'm showing in a simplified on the sending end side, receiving end I'm showing here. So here the AC is coming at a low voltage, and then AC is being converted to DC with the help of IGBT PWM rectifier. And this is a two-level converters, not the 3-level converters. See the speciality of the system here. 2-level IGBT converter is such a high voltage, and hundreds of IGBTs are in series and parallel combinations. And as I said, this is a 3-phase IGBT rectifier, and we have a similar unit on the other side, which is converting DC to AC and connecting to the main German grid. And this is called the ABB HVDC light. There are 2 or 3 more installations like these. And world's largest offshore wind park connection to the German grid. And this is using 2-level IGBT converters at each end, series parallel connection of IGBT modules, sinusoidal PWMs, rectifier and inverter, both are using at 2 kilohertz sinusoidal with the IGBT. You can do that with a 0 sequence injection to improve modulation factor. Now what is happening here on the sending end, that the on-load tap changing transformers automatically changing so that the modulation factor is highest. And here also, this is sinusoidal PWM, not displaced vector PWM. and then they're using zero sequence in order to make the maximum modulation factor is 0.907. So with the maximum modulation factor, the DC voltage is maximum. With the highest DC voltage maximum, the efficiency of the transmission becomes high, and also you have a maximum P capability, P power capability. And transformer on-load tap changer improves conversion modulation factor and the features, because it's the PWM converter, this is HVDC grid actually, with the 450 megawatts. Because the PWM converter, you can control not only P and also can control the Q, the reactive power on both sides. And the DC converter system like these, voltage fed, the traditional is a thyristor type current fed converters. You can have a multi-terminal capability. You can have a bus voltage regulation and the flicker controls, improvement of AC system stability by fast transient controls, and of course the underground and undersea cable transmission has some special advantages of that. So you can see this is a very recent installations by the ABB. ABB invented the IGCT, integrated gate commutator thyristor. They are not using IGCT for high power application like this. They're using IGBT. IGBT is becoming much more important nowadays, not only medium power, high level, and trying to beat the IGCT. It has a what we call the smart power capability. And here particularly hundreds of devices are in series, parallels, and with the help of switching controls, they can dynamic sharing of the voltage, a lot of advantages because of smart pair. So they're using the IGBT, not IGCT. And possibly that IGBT was invented by an Indian, Baliga, Giant Baliga, he's in North Carolina State University. He got the President's Gold Medal very recently as a result of that. And IGBT is becoming very important device. So in brief, this is the system. You search the internet, you can get all the information you can get from the internet. In fact, this is again a Japanese Shinkansen system, the bullet train in Japan drive system. So it takes a 25 kV power supply, and then it has a rectifier, PWM rectifier, and a three-phase PWM inverter with the IGBTs. It is a three-level inverter. You can see here three-level inverters. Multi-level inverters are important nowadays for high-power applications here. And then every unit has 4 induction machines in parallel operations. So when you're trying to design such kind of systems, you have to be very careful. The machines have to be matched properly. And then also the wheels they drive, each machine is going to one axle drives, The wheels have to be also very matched. Otherwise, the share of the power will be quite different here. Let me talk a little bit of these things here. Yeah. The DTC controls, is a very important control in Europe. There are 2 kinds of controls in the AC drives that are being dominant. One is the vector control or field-oriented control, as you know, and the other is called the DTC control, the direct torque and flux control, invented by Japanese scientists here. And only the ABB company in Europe, they are commercializing these things, these kind of drives for high-power drives, of course. And this is an example of ACS 6000 drives, a converter system. You can see the very familiar converter. The lower one is a multi-level using IGCT. This is the ABB. You see the IGCT and PWM rectifier, PWM inverter, and it is a 4-quadrant drives on both sides. And the upstairs, the upper one is only diode rectifier in the front end. And on the other side, it can be induction motors or it can be one field synchronous motors. Either of the 2 drives. It can be also multi-motor drives. In fact, they are using these ACS 6000s in conveyor controls in Andes mountains in Chile. And there are some problems there, some failure problems. And I was asked to be a consultant for that project. But what happened in the Andes mountain is 15,000 high. And I have to fill up the forms, and they say I'm so old. No, you cannot go to 15,000. It's too high, breathing problems. So I was finally disqualified because I'm not young enough to go upstairs on the 15,000 flights anyway. So this is again a commercial drives for high power applications like conveyors, belts, and mining hoist, and those high power drives. And this is the summary of the features of the ACS 6000 drives. The world's DTS control medium voltage synchronous motor drives, applications, mining hoist, conveyors, pumps. The ABB is a very big company, and now they sell all over the world. They have different series of DTC controls. This is high power ones, and 3-level PWM with the IGCT devices. PEB module. This is one trend of the power devices. The converter trend is a PEB module. So see, if you look at these are individual blocks you can buy, and then connect together. It's called PEB modules, the power electronic building block. People are essentially going away from the regular designs, are using PEB modules and just connect together. So they're existing and they're integrated bypass diodes, so put it together. Now traditionally these type of drives use cycloconverters, but cycloconverters are now obsolete. And it is the voltage fed PWM that is becoming very common here. Let me talk a few words about these. 10 MVA 3-level converter system for rolling mill drives, manufactured by Mitsubishi. Again, this is a GTO drives, GTO PWM. Today you use it, do not use GTO, maybe you use IGBT. These are 3-level inverters, these are 4-quadrant drives here, and these are one-field synchronous machines. Normally we prefer synchronous machine for drives. If the power is a little bit lower side, it will be on the permanent magnet machines. At high power, it will be one-field synchronous machines. Synchronous machines has a higher efficiency compared to induction machines. That is one motivation for using. But synchronous machines, this is the vector control drives. Both sides are vector controls. And vector control for synchronous machine is a little bit more complicated with the one-field synchronous machine rather than induction machines. But it shows in the kind of block diagram forms the vector control for both the PWM rectifier and PWM inverter. And because it is a rolling mill, you need to have 4-quadrant controls, high response, high pulse response, and energy flowing in either directions. This is very interesting projects in the axial flux PM module, direct drive for electric vehicle drives for vector controls. I like to skip this. As I said that these view graphs, these slides, if you have any questions on these, anything, just send an email. I'll be glad to answer all these questions through email, or short questions here. So this is actually next generation drives. This is the axial flux PM machines. That means the machines going through each wheels, two last ones, these are the next one, the two last. These are again my projects, this is the fuzzy logic based optimal control of wind generation systems. Now, as you know, I don't know whether you worked with artificial intelligence, which includes the fuzzy logical neural network, is essentially the frontier technology for the power electronics and motor drives area. And we have spent a lot of time in our university to work in this area. So it was one of the student projects actually, This is the wind generation project, but it's funded by the government actually. So it is on the variable speed on the left-hand side. This is the cage machines and the bidirectional 4-quadrant converter system with IGBTs. And these converters, I can see the energy can flow also this way, and it can control the unity power factor on the line side. And these have a local side is a vector control drives here for this one as well as this one. And on the outer side is a fuzzy logic controls here. One fuzzy logic control, optimum power surge FLC1. Basically, in a wind generation systems, as the wind speed is always varying. As the wind speed is varying, the generator speed has to be controlled to follow the wind speed so that the aerodynamic efficiency is maximum. So what we do here, we have a speed command. We do by such meaning we set a speed and see what is the power coming out from the wind generation systems, and we incrementally change. It's called like a maximum power point tracking, MPPT, in a photovoltaic system, and change the speed and see how the power is maximum, higher or lower. So in that way, by such techniques, online such techniques, we gradually change, ultimately we settle down the maximum points. That is called online such methods. So that is one fuzzy controller there. And there's another one, the FLC2. This is a excitation control by fuzzy controls. Machine is normally always a light load. So as a result of this, what we try to do, we control the flux of the machines. At light load, efficiency becomes higher with a lower flux. We call it programmable flux, light load, efficiency optimization. That's the name which we use. And we again change the flux, and see the efficiency, see how much of power we generate. So we do by trial, online search basis, and try to maximize the efficiency or maximize the power output from generators. There is another fuzzy control as FLC3, we call the robust controls. Fuzzy logic control gives you robust control. So within the speed control loop, because the wind turbines, it often gives, because the vortex of the wind gives a kind of lot of burst of energy, so kind of pulsating torques, So what we call the robust control is the kind of things you use, and fuzzy control is a very important tool. So robust control, I don't know, do you work with the fuzzy controls? Okay, we have done it. This is a Brazilian researcher. He was a professor, came to work in my university, and a number of years ago, we finished these projects. And okay, this is a kind of showing the operation of the fuzzy logics, how improvement of aerodynamic efficiency improves the output power, corresponding speed, and then jump of the power for the excitation controls. So the operation on the wind velocity curves at different speed, and our goal is to maximize the line power output. And FLC1, FLC2 fuzzy controllers, one after the other in sequence, try to control these things. The last example I want to, for neural network applications, I don't know whether you are familiar with this or not, but they will give you at least some ideas of the neural network. Our problem is that in a machine drive systems, the feedback signals, we want to compute from the line currents and voltages. So we sample our line currents and voltages, and we have a set of equations from which we make calculations, the rotor flux, then the unit vector, cosine theta e and sine theta e, and the torque. So these are the equations for computations. This is the kind of textbooks. How do you compute these? So normally a DSP do all such calculations and to do this. But here, instead of using a DSP, we'll use a neural network such computations. Neural network can do such computations very well. And we want to use static feed-forward neural networks. Feed-forward, or we call it back-propagation networks, is a common name to use. And where we want to do this is, what we basically do is, these equations which are being solved by this neural network is just shown here, and is showing a 3-layer neural network. So from machine terminal voltages, we integrate the machine voltages and calculate the fluxes and the IDS and IQS, right, the input, and then solve these equations in order to get the desired output, the same output like a previous curve. So the idea is to use a FPGA or a simple ASIC chip in order to make such calculations instead of giving you a DSP. Just a simple example, this is also one student project a number of years ago. Now this is a standard, we call it backpropagation networks. In a MATLAB, there's a neural network. Toolbox is there. I'm not sure you're following or not. Toolbox is there. We take help of the toolbox in order to design these things. Now, in order to use a neural network, in order to design a neural network, first in the beginning, you need to have a training of the neural network. So you need to have example data. So in the computer simulation, you create an example input-output tables. For example, an input, this frequency may vary widely from, say, 1 hertz to 100 hertz, fraction of a hertz to 100 hertz, and then in every cycle, then every few degrees. So you have a input and the corresponding output for each of the input, and these data from the simulations, these data are used for training the neural network. So that is one very important feature of the neural networks, that in the beginning, from the example data, it will train the neural network. And after training, you design the neural network and then use it with an FPGA. You can also solve with a DSP also, but it is a parallel computations. A DSP will slow out, so the FPGA is kind of things a better solution for this. So this is a 424 feedback signal estimation of direct drives. Now we are coming to a kind of conclusion, so maybe I will spend a little more time on these. I have two figures here, one conclusion and a future scenario. Now in the beginning, as I said before, the power electronics has been established as a major discipline in electrical engineering. Importance is not less than computers and information technology today. This is very important. It's becoming so important that it is tending to surpass the computers and communication technologies there. Now, technology advancement, cost and size reductions over the number of years of research and research here. They're now promoting the extensive applications of power electronics, industrializations, high energy systems. So this has happened as a result. The cost has decreased, size has decreased as a result of technology advancements here. As I also said in the beginning, the shortage of fossil fuels and environmental regulations will increase cost of energy and thus promoting energy savings by power electronics. Energy saving is one of the big things going on right now. Wide growth of environmentally clean renewable energy sources. As I said, but photovoltaics and wind energy systems, they use extensively power electronics and going on all over the world. Recent study indicates that renewable energy alone with the storage can meet all the future energy needs of the world. I mentioned that well. And again, the last one I'm talking about the wide growth of battery electric vehicles due to petroleum shortage and environmental pollution problems. So these essentially I said along my presentation all the times, but I'm trying to summarize. Now this one is a kind of important one. The technology as it is, the power electronics and motor drives, I could not talk much about these in my presentations. And here I'm trying to summarize in a few words here. We are seeing the trend that the IGBTs are now being the most dominant among all power semiconductor devices. The GTO is already obsolete. The bipolar junction transistor is obsolete some time ago. IGBT was so long as a kind of medium power and gradually inching forward in higher power. But right now we see the big companies like Siemens and ABB, they're using IGBTs in hundreds of megawatts kind of applications. So suddenly you're seeing the Dr. Baliga is a kind of hero, all over the world. He's considered as the father of modern power semiconductor devices. Do you have heard the name of Baliga? It's okay, he's a very famous name in the United States, We are also seeing that the large bandgap power devices are going to bring renaissance in power electronics. Most of our devices are silicon-based devices. Now, the new devices are coming up with the silicon carbide devices. They are just coming up. They are just being introduced to the market. These devices has a higher temperature compared to silicon, the lower switching loss, and even lower conduction loss. As a result, they are just coming up, only they are more expensive. The reason is that the purification of the single crystals are a little bit more expensive. But these coming up, a PowerX company, for example, in the United States, they're putting in the market half-bridge voltage fade converters with the silicon carbide, 15 kV, IGBT is now in the research, and then GTO and all these devices. These large bandgap devices are particularly important for utility system applications. Utility system applications like HVDC, the flexible AC transmission systems, UPS, and then STATCOMs. I don't know if you're familiar with these names or not. The high power utility systems all require high power. So high power, these silicon carbide devices are very important. And also high power drive system as well. We need to have these devices. Voltage fade converters are becoming more universal. Cycloconverters are no more. Current fade converters are essentially going out. All the systems, modern, all voltage fade converters. Multi-level converters in high power are becoming popular for high power drive utility systems. Multi-level converters, particularly 3-level converters. We call it diode clamp converters, I showed you before. There is another category called cascade edge bridges. This is also very important and a lot of applications also in utility systems here. Converter technology has the trend of VLSI technology. Integration, automated design, simulation, fabrication, performance test. The detailed design of the converter is essentially going away. You want to design the converters, you do for high power converters, the PEB modules, the power electronic building block modules, and low power is the power integrated circuits. The whole converters, everything will be kind of just like an acid chip, they are all integrated. Converter, controller, machine will tend to merge intelligent machines, particularly low power inter drives. Converter size is a machine, converter and control is very small. So why not have machine with the converter and control is single unit. Most of the machines require variable speed drives, most of the machines. Vector control will be universal in AC motor drives. You have scalar controls and vector controls. Scalar controls, the DTC control I just gave illustration. the Europeans are very biased with DTC control. I recently wrote a paper in which DTC control, I didn't talk much about that. It gives a kind of pulsations, kind of pulsations of the current and torque kind of ripple is there. But it is simple, it has a lot of advantages. But the vector control is the superior kind of things and all controls here. So that I'm saying that there will be no more scalar controls because now all the drives use DSPs and even the most simple open loop horsepower control use DSPs. So when you're using DSP, the complexity of the software is not a factor at all. So vector control is more complex than this scalar control, but the complexity in software is nothing, just extra lines of codes. So that is the reason we are saying in future the performance improvement vector control will become universal. Increasing emphasis on incremental application-oriented R&D in power electronics. We are saying that a lot of research and developments in incremental research. You see, we say again, it may not be true again, but at the same time we are saying most of the major research like vector control, DTC control, multi-level converters, topology, and then sinusoidal PWM. All these technology developments have been mostly done, and then we can incremental technology development. And we are seeing that as lots of papers are coming up in transactions and even in conference proceedings, but mostly they are small contributions and kind of application oriented. So we expect to see more of that. Power electronics and drive technology is tending to mature and emerge as a high-tech frontier in power engineering. This is very interesting, In the United States, when we used to do developments in power electronics is a high-tech technology, and power engineering we call it low-tech area. Now power electronics is merging with the power area. It is like a high-tech frontier in power engineering. In our department, University of Tennessee, we have a very big power engineering department right now. And the power electronics is considered as a kind of component of power engineering. We are not identified anymore. So I always say in the conferences that power electronics engineers, they are so proud of the discipline, now they are losing identity. They are being defined as a power engineer because it is essentially a component of power, that's the important thing, the high-tech front. And another thing we are noticing is that the power electronics, power engineering, including computers and communication, information technology, they are tending to merge together. The kind of high multidisciplinary technology is being born here. Particularly as a result of smart grid. Smart grid is an integration of these advanced technologies. And after the smart grid, projects will go on for some time. And a kind of new advanced integrated technology is coming up in front. That is, as I said, the merger of all these component technologies. That's the kind of future training. Okay.
I think we can take one or two
questions.
Yeah,
sure. If you have questions.
He said some methods like energy storage methods, battery storage and hydrogen storage. Of them, which can be the better one, considering economic wise?
Okay. Traditionally, battery storage has been favored. Is the most convenient form storage. In a battery storage, as I said, that AC cannot DC store it and then it power. But it's also very expensive. So in future, we are expecting the battery storage will be the most common kind of storage, and technology developments, particularly the battery is very, very expensive here. And already the flow, the call it vanadium, VDX battery, vanadium redox flow battery is a kind of new battery has been developed by the University of New South Wales, and this is being used for bulk storage for high power. But the batteries technologies for these are kind of complex chemical plants. They have a electrolyte is circulating with a pump at temperature, metering, it's a kind of complex installation. So research is going on, and eventually. So what I'm saying is that the battery storage is the most common future energy, but a lot of obstacles for the cost point of view has to be solved here. But the same battery technology is for electric vehicle also. So there's a kind of commonality is there as a storage device. And pump storage is convenient. If you have a good, favorable site, then it is very convenient. But otherwise, if it's not convenient, it can be expensive as well. I don't know. The other, like a superconducting magnetic energy storage, that is very expensive. Ultra capacitor, I showed you, that is also not very well developed technology, is still going on, not very I think that's all what I said.
The hydrogen storage.
Okay, hydrogen storage, yeah, because hydrogen storage is a very good way and abundant wind energy, but as you said, hydrogen storage, convert the wind, or photovoltaic wind is the most common, convert wind energy into electricity, okay, with the wind turbines and everything, and then electricity used for the electrolysis of water to generate hydrogen. So you see the multiple energy conversion, the efficiency is poor, expensive also, but convenient. So we cannot really say only one type of energy will be unique and nothing else will exist. It depends on a lot of circumstances, you know. So hydrogen energy storage is also good way of doing it, expensive, efficiency less, but in some cases it will be viable. Energy storage, if you have to have fuel cell kind of energy plants and all these things, so you need the hydrogen gas as the fuel. So there, the generation is hydrogen. But if you talk about the future hydrogen economy, as I just mentioned, you need a massive storage, hydrogen used for everything as a fuel. So that will be kind of much future, with a big question mark, whether it will be possible. We are trying to see, even technology-wise in the universities, we try to see all possible. So you don't, in the beginning, we don't talk about the cost or anything. We see what can be feasible or not feasible. Because any technology, it is born, and then gradually iteration, research, finally it comes down. Price comes down, everything comes down. So that is the concept here. Is that the question? Any other questions here?
Trade with the reliability of power electronics.
Oh, reliability of power systems.
Power electronics.
Power electronics, okay. That is a good question. We have argued all the times what about reliability of the power systems. The example is the electric car. You have power electronics there, you have mechanical system, common mechanical system. A lot of people blame power electronics. If you use a variable speed drive in a big, for example, in a power station, you use variable speed drives for induced draught fans. A lot of people are simply afraid about the reliability of power electronics. If you use power electronics for variable flow controls, it might fail and shut down the power plant. The answer of this question is that you have to design it very well. If you do not design very well, and equipment design is a very important art, and you have to design very well. If you design very well, we take typical price around 20 years, the typical life of the power electronics equipment. But you have to design it very well. If you design it, it will go longer. And also, temperature is one of the killers. So, all the components, you have to be, if you design below, with a lower temperature, the lifetime is longer. But then it will be more expensive, So that's kind of trade-offs are there. But an engineer who is designing a power electronic system, whatever applications, he has to be a very mature designer. He has a good knowledge of the components. For example, the passive components like a capacitor, if you use an electric capacitor, that is the lowest life in a variable speed drives. So in some systems, for example, when I first came to GE to design electric cars, we did not use electric capacitor initially, we used AC capacitors. Because AC capacitors have a longer life, although it is more expensive. So these are the techniques, you use to improve the life of the equipment, and then you have to pay by the price. So that is the kind. So there is no unique life. Again, as I said, typical life is around 20 years for the power electronics. Particularly if you are designing a big equipment, a large multi-megawatts. A team of people normally do the work in companies like Siemens and ABB. A team of researchers, they do consultation all the times. The EMI is one of the very big problems. You take good care of these. Temperature is the most important problems. And if you have a forced cooling, all these big converter systems, I say all is forced cool, water cooling system, water cooling. So the cooling system should not fail, or temperature should stay within a certain limit. So these are all factors, a kind of complex kind of things,
If there is no question, I think on behalf of IEEE Bombay section and Systems and Control Engineering Group IIT Bombay, we thank Professor Bose for presenting this illuminating talk on energy scenario and impact on power electronics. I hope that he will visit Bombay and India again, and he will present such a talk. Now I will call upon Professor Khabarde, who will present a memento on behalf of IEEE Bombay section.
Thank you very much.
I will call upon Mrs. Lalpriya on behalf of Systems Control and IIT Bombay. We present a small memento to Professor Bose for this. So we conclude the session.